All right, good afternoon. I'm going to start again. My name is Chris Cooper, and I'm here from Skidmore, Owings & Merrill. We're an interdisciplinary practice, architects, engineers, planners. And we have an idea that we want to talk about today, and I'm really appreciative of all of you being here and also being in the Buildings Pavilion with this topic. And I start with the premise, the realization that cities cover a mere 3% of our planet's surface. Yet, they're responsible for more than 75% of global emissions. And this will continue. Population is growing by more than 2 billion by the year 2050. So this is a conundrum. The built environment is a primary contributor to global emissions, and we continue to build, it continues to grow, it continues to expand. So we've set targets as an industry, we've set targets which we're challenged to meet. And what I want to say very clearly today is that the target of net zero simply isn't enough. It's not going to change the curve. So can we think beyond zero? Can we go beyond net zero? So this premise would say, can cities, instead of being the primary contributor to global emissions, can cities become part of the solution? We believe emphatically yes, that buildings can actively absorb carbon and that buildings can perform like trees. And this was our provocation at this pavilion last year at COP27. We made this provocation, can buildings act like trees? And we proposed that with current technologies, with a combination of biomaterials, nature-based solutions, and active technologies like direct air capture, we could absorb more carbon than we emit. And this idea received tremendous support. And we've spent the last year focused on developing this idea, a very specific idea with engineers, with carbon specialists, with architects. And so we've been working to shift from concept really to reality. And what I want to share today is focusing on one specific building typology. So focusing on tall buildings. We've taken tall buildings, high-rise construction, as an important solution to urban density, but also as one of the primary contributors to carbon emissions and also one of the most challenging to address. So in order to do this, this is a scalable idea from small to big. We're focusing on tall, and that scalable idea means that we have to shift our thinking. We have to shift our point of view to think about buildings not as a static compilation of materials, but as living organisms themselves, living, breathing organisms. And we have to look at them holistically and think holistically about a dramatic reduction of carbon in the buildings to begin with. Also thinking about maximizing carbon sequestration and extending the lifespan of those buildings. So we, in this process, asked ourselves a series of questions. And these are simple questions, but they're questions that you have to ask every step of the way in designing, from the smallest decision to the largest decision. But as we're working on a holistic design, just how low can we go relative to embodied carbon, upfront embodied carbon? How far down can we take that? And also, how low can we go relative to the active use of energy in the building? And we also make the point of, okay, opposing that, then how high can we go relative to carbon sequestration? Can we actually sequester more carbon than we've emitted? And how high can we go relative to energy production on site? And finally, we ask ourselves, just how long can we extend the lifespan of the building? Can we go beyond a conventional 60 years? Can we go to 100 years and really expand that whole life carbon cycle? So this is a snapshot of what I'm going to share today and what we want to talk about. And it says that we can reduce the baseline carbon, embodied and operational, by 100% 5 years after construction. And within 60 years, we can more than double that. And then 100 years, we can more than triple that. And this takes into account the realization that many building materials and building systems can't last 100 years. You have to replace them over time. And so this is a scenario that we actually can make dramatic reduction at construction, and then past construction, we go to 3 times the original baseline carbon. So how do we do this? What are the specifics of this? First, we have to think very specifically about how we're building today. And today, all construction, and particularly high-rise construction, is sequential. And it is designed even by independent groups. Each system is designed independently, thought about independently, and added one after the other. And even built sequentially, which means that you're adding carbon footprint on top of carbon on top of carbon for each of these unique different systems. So can we flip again this thinking? All of this is about inverting the conventional. So can we actually think about an integrated approach? Can we ask each system to serve more than one purpose, and maybe even 3 purposes? And so can we think holistically about all of the systems and bring them together to overlap in their use and in their function? So very specifically, this is conventional high-rise construction today. Concrete slab, part of the superstructure. Then mechanical systems come in, they're distributed under that slab. A false ceiling that covers that. Sometimes we add a raised floor for wire management, like you see here today. All additive components. So we're proposing a new way of thinking that inverts this system and compresses this, which allows us to significantly reduce the amount of material in that structure. And then we have a raised timber floor that creates a cavity between that becomes the space for an integrated ventilation system. So we're taking what is the conventional additive process, inverting that to a completely reductive design, consolidating and in some cases eliminating systems. So reducing the amount of material and reducing the systems and reducing the embodied carbon. So let's look at that specifically. If we think about the MEP system that's typically run in ducts distributed from space to space, where we are proposing a pressurized floor. It's done today, it works quite well. And so we remove essentially the duct network. We remove the false ceiling that's concealing all of the systems. We remove the additional raised floor for wire management. And we significantly diminish the depth of the structural slab and the material in that structural slab with the vault structure. And we remove construction waste. And that happens because we think of this as an integrated modular shell structure. And so, the amazing claim is that we can reduce embodied carbon, upfront embodied carbon, by 70% from the conventional high-rise construction. So I said modular, and this is a really important part to the superstructure. The superstructures are often one of the greatest offenders of carbon, or the greatest holder of embodied carbon. And so we're proposing a modular system that is cast off-site. And the cast off-site is a fundamental because it means long curing times. And those long curing times, it's the perfect opportunity for that. Integrated PV panels on roof or in facade, as well as solar glass, allow us to have, depending on to resist, is the wind load. Right? That's the greatest offender structurally to a tall building. And so how can we work to reduce the wind load? So quite simply, we're able to remove cutouts in the building, strategically placed, that literally confuse the wind flow around the building. And those cutouts can become active outdoor spaces or amenity spaces. So what we're proposing is to use the natural building physics, to use the natural airflow, And this is what's very important, is that we can introduce, because we're a tall building, we can introduce direct air capture into the building and use the natural airflow to our benefit. And so now we are truly carbon positive. So that natural stack effect filters in, pulls air in and up through direct air capture. We don't have to run fans on the direct air capture. We use the natural flow of the building in order to literally filter the air around us. So we now have a breathing building. And as we ask each of these components to do more than one duty, our cutouts, which are reducing wind load, really are outdoor gardens. It's an opportunity for us to introduce biophilia, introduce outdoor space to users. So last component of this is recognizing that the lifespan of the building, not tear the building down to build a replacement. That extends the whole life carbon cycle. And that dramatic to a flexible office space to the first carbon absorbing hotel. And this is a fundamental in relation to thinking about floor to floor heights and lease spans. So I want to look quickly at the numbers, and I think what's important to understand without getting into the specifics is that this is not a proposal for a great structural idea or a great mechanical idea. It's a combined holistic approach, embodied in operational carbon in a tall building through all of the decisions and ideas that I just put forward to get down to, in 5 years, 100% reduction. And again, in 60 years, more than double that, and in 100 years, more than triple that. So we show an idea of a system, a single tall building, but it's really not meant to be a standalone proposal. That this idea can accommodate buildings of varying heights, can accommodate buildings of varying programs, that together work to make a single carbon network, to make a carbon absorbing forest that can transfer our districts and our cities into a single carbon network. And so I show you that we have flexibility of height, flexibility of program, flexibility of size. We also have flexibility of aesthetics as a system. We think this is an implementable idea today. It's a real idea that gets us past what we're seeing on the charts in these walls. And I'd stand here as part of a really large team that's been working together, of advisors and an interdisciplinary team. And the point here is that the team has to broaden beyond us. And so we really do think that this is an implementable idea for now. And I'd like to share with you a summary video, and then I will conclude. The volume. Use the microphone. High tech. Hold it here.
Aywa.
I see.
What if our buildings were more like trees? Last year, SOM posed this provocation as the concept for Urban Sequoia, a building that absorbs carbon. And for the past year, we've been developing this concept beyond a building into a holistic design approach. We asked ourselves, How low can we go in emitting carbon in construction? How high can we go in carbon sequestration? And how long can we go in extending the typical building's lifespan? Tall buildings are one of the largest and most ubiquitous building types in our cities today. They are also additive by design, starting with the structure, then adding multiple materials and systems, which increases embodied carbon and lowers efficiency. We need to transform the tall building into a tool to heal the environment. By reducing the mass of our structural shell, inverting and consolidating systems, and using revolutionary building materials, we achieve a radical reduction of carbon and waste. We also generate clean energy on the facade by using technology such as solar glass and photovoltaics. We go further by using stack effect currents with direct air capture technology to remove carbon dioxide from the surrounding air. Lastly, we extend the building's lifespan from 60 to over 100 years by making the design more timeless and flexible so that it can adapt into the future. SOM's new approach removes 100% of a building's carbon emissions within 5 years and continues to absorb over 300% of carbon throughout the life of the building. This approach can also be applied to many different building mechanical systems. It's no longer a vision of the future. It is a holistic approach that turns concept into reality.
Hi. That's very loud. Hi, I'm Ryan Kolker from the International Code Council. You mentioned at this point it's largely conceptual, but how are you bringing some of those elements and concepts into existing projects that you guys are working on today?
Yeah, it's a great question. You know, can this be broken into individual components, or does it have to be holistic in its implementation? And for certain, all the ideas can be brought into every one of our projects in the simplest way. I mean, just simply, we can ask when we're working on a conventional project, is this decision the lowest embodied carbon we can put into this system? And we can ask ourselves those simple questions: how low can we go? How high can we go relative to on-site production? And so I think that the decision structure is fundamental in how we're working today. But I do want to stress that I think that this is more than that. It's a comprehensive idea that we have to kind of flip some of the conventional construction techniques and questions in order to make something so dramatically different. And I think that these systems are not unreasonable or not out of bounds today, but they do have to be kind of thought about holistically. So if we're going to do a raised floor, it should be with displacement air. Can we actually flip the slab? And I think are there code issues that we have to work through that to ensure that we have the right fire separation? So I appreciate that you're here watching this, because these are the types of questions that we have to really push ourselves on. We think that the answer is yes, that this is all achievable today with current codes and with current systems. And so to answer your question, we ask ourselves the fundamental questions in every decision, and we are beginning to think about implementing certainly low carbon, but even carbon positive materials into buildings as they starting to become available and actually on the market. But what we're most excited about is making a grander, more fundamental shift in the construction process. And I think that this is it's we call it a prototype, but once we start building these, that they can become much more standard and simple. And the only, the difficult piece, or maybe the expensive component, has to do with the technology. And I think that if these technologies can be implemented into buildings today, then the price point comes down. And it's worth, making the analogy to the solar industry, and that one used to think that you had to have massive fields of solar arrays, and it was an expensive infrastructure expense. But now we see solar panels on the most simple house, and so through implementation, it has gone to accessibility at all scales. So we think that the specific technology of direct air capture can have the same momentum.
Thank you. My English is not very good, so I try my best. You use the word holistic from conception to build the building. If you take the part of conception and the part of building, the building, what is the part of conception, holistic conception, and the part of building the building itself? The time it takes.
Oh, how much time does it take from concept to reality?
Yeah.
Great question. I think that this, it depends in part on the scale of the operation. But there's no reason that the work from concept to reality can't be conventional construction schedule. And so, with for a large scale project, you have a year and a half of planning and then implementation. But there's no reason why this can't be following similar construction timelines for tall buildings.
So you mentioned two things. One was you touched briefly on cost. And so just wondering what kind of cost analysis ROI you're looking at for, say, prototype, what that might look like. And secondly, in terms of systems, have you looked at the water systems in this integrated process of rainwater capture, black water, gray water, reuse, and how does that become part of the whole ethos of the Sequoia? That to me is interesting of how far you've thought about systems.
Right. Two strong questions. And the first is the cost. And I will say that we have not done the initial ROI on the project. And so we think though that we are at the point of development that we have enough specifics that allow us to do that. And so this is a fundamental next step for us. Relative to rainwater, or to water in general, water conservation. So one of the interesting components of a tall building is that its footprint's quite small. And so it is difficult to think of capturing. It's not often a very effective tool for tall buildings to think about capture and reuse of rainwater. But in a building like this, one can think about a circular system. And I think that also becomes part of back to the living building, living organism. We have to think about a circular system for water within the building itself.
So, hi Chris, thanks for the brilliant presentation. Mohammed, I'm Mohammed. I met you a few minutes before your presentation. However, I do think that you have to consider the urban microclimatic effects of the whole site when you are talking about such a building which acts as a sink. So, first of all, I think we have to calculate the whole site carbon emission resources and how much is it in order to refine your building allocations among that site, so that we can really consider, we can really say that this is a carbon capture machine, sink, whatever you can say.
Right.
So that I do recommend you simulate the whole site with your intervention designs, Such buildings cannot be only considered educational, residential, whatever. No, I think for the first of all, it should be considered as a carbon sinks, a solution at the urban scale that can be connected to the urban microclimatic and meteorology conditions, which is directly connected to the planning, to the urban design of the site. I think in that direction you can shorten the time distance between the concept and the execution, the application.
Several good points, actually. I might just parrot some of those, because I think one point was you have to first consider unintended consequences and do the analysis on a broader scale of those potential unintended consequences of a carbon sink. That's one point that I feel that you've made, which is an important analysis component of this, is as you aggregate these. I would like to also point that I think the key is aggregating these and not thinking about singular buildings, and also really not thinking about singular building types, and that this concept of absorbing can be applied from the smallest house to the tallest building, and that it's just a way of thinking, and so we can find analogous solutions for a single house, different solutions but analogous solutions. And so ideally we work to make a whole city, a whole district working together, and even work with the spaces between the buildings. What is the paving? What is the natural landscape? Can we think of designing a whole ecosystem of carbon absorption rather than carbon production?
Sure, I agree with that, but I also stress and add that when I mentioned the urban microclimatic conditions, I mean, the urban canopy layer, which is the building roofs. When you put such tall building, you by default make a mixture, a circulation when the wind hits that tall building, and vortices can be generated. That's the mixture between the layer above the urban canopy layer and below it. The small buildings, the single housing, can lead you to a prototypology for the urban form design that can have your solution.
That's clear.
Thank you very much, Chris. A really exciting presentation, and it actually links to some work we also do on how low can we go, indeed, in building projects. And I have a question to you. What needs to change in the market so that these types of projects can actually be reality? Because you're saying this can happen today. I don't know if all of it can already happen today. I'd like to be curious about that. But what needs to change? Who do you also need to convince so that this actually will become reality?
It's when we made the presentation last year here, this was the number one question. How? What needs to happen in order to make this buildable? So we think that we've taken a big step to think about primarily conventional construction techniques that can be implemented today. And so I want to stress that we think that without change, one could build the first urban Sequoia. That it doesn't need to be a change in technology, doesn't need to be a change in the market. One can do this today. Now, there are additional costs associated with it, particularly with the direct air capture. And so this actually is not unprecedented to add direct air capture onto buildings. And so, but it would be the first true integration of the natural airflows in the building with direct air capture. So that's a progressive idea. And to incentivize one to do that, certainly policy tax credits, which exist in some places, could help incentivize the incorporation of technologies that aren't fundamental to the operation of the building. that's probably one of the biggest hurdles to get past, is that the incorporation of direct air capture is not fundamental to the operation of the building. And so in order for buildings to become the armatures for direct air capture, there needs to be that shift of purpose and a demand on the building owners and the building industry to think about incorporating that. And there are so incentive structure for that would probably be the most fundamental. But the construction, the ability, depending on obviously where you are, but in certain areas, the construction technologies are all entirely available today.
But even if we don't look at air capture for now, some of the other things you showed, from business as usual, how we build today,
Right.
to this new paradigm, which is exactly also how we show it in our work, the reducing of materials and stuff, because
Great
it's in
question. It's a great question, and I you know, we often as designers, we often put blame with others, with our clients, with the market, that the demand is not there, and some of that's very true. But what we are seeing, which is actually shocking, and this is in pockets, right? But we're seeing clients that you would never anticipate asking the question, asking at the very beginning, how can we reduce our embodied carbon footprint? They have ESG reporting and targets that they've set for themselves that they don't quite know how to get to. So many of the world's corporations are setting targets that we can help them get to. And so the dialogue has completely changed relative to construction. And so we are having this conversation now. You're right, making some of the hard decisions to actually make the flip is not happening today. I don't have one of these projects on the drawing boards. That is absolutely right. But we have many projects on the drawing boards where we are asking about reduction, and we are calculating. We calculate the embodied carbon of every one of our projects today. That's an amazing statement that you would not have heard 2 years ago, 3 years ago. We're calculating that in real time as we're designing. So in schematic design, we're setting targets at the beginning. In schematic design, we're calculating embodied carbon. We're certainly running energy models, which has been happening for a while, that we've been seeing what the operational carbon is. And so, but we are doing that for 100% of our projects. And so we're trying to loop that data back into the design. So my point is that a lot is happening, and that there is
carbon of all your projects. Are this information, or are you planning to put this information available to kind of the broader community, so that we can establish more benchmark and then giving the confidence of what is a reliable target that we can achieve?
Yeah. That's a great prompt. And because today it's not public for us, but we are starting to talk about it and starting to release it. I just gave a lecture on embodied carbon in facades at a facade conference, and we showed 2 facades, 2 buildings that we're working on. We showed how we're calculating the embodied carbon, and we showed how we're calculating the operational carbon, the heat gain and loss of that facade, and we put the numbers on the wall and said, this is what it is. This is what we're learning. This is what we're learning when we design an aluminum facade. This is what we're learning when we design a terracotta facade, and put them side by side, and they're talking about them. So I think this is the right prompt, and that we will. So I'm going to take that as a point that we should be pushing this out. And I think that the more we push it out, the more conversation that happens like this between all the different groups that are doing this. So I think that it doesn't serve us to keep it to ourselves.
Agree.
One thing I'll add to sort of Roland's question about what are folks doing today. I think one area that's increasing in activity, but hasn't necessarily gotten the sort of attention on its carbon impact, is prefabrication or off-site construction. So we're seeing a very significant increase in interest, and certainly development of tools like codes and standards to really help support that.
I think that's a really great point. There's momentum there, and we're really starting to even see you know, as we think about new buildings, that becoming part of the conversation very early on. Because it also requires designing with that in mind. That it doesn't help when you design the project and then think about modular after the fact. All right, well, I'm really honored to be here. Thank you very much for attending, and thanks very much for the fantastic questions.